and I'm a master's student at Western Michigan University in the United States. And today I was given the privilege to present one of our exciting projects that we recently finished. Our team is the Center of Advanced Smart Sensors and Structures, and the topic we will be presenting today is strain sensor fabrication by means of laser carbonization. So the outline for today's talk, we'll start with an introduction explaining some strain sensors out there and different techniques. Then we'll do some strain sensors and printed electronics, followed by the laser parallelization process and how it works. Then we'll go into experimental, so the materials we use, the design, fabrication of the strain sensor, and the experimental setup. Then we'll do the results and discussion, followed by the conclusion. So strain sensor applications, there's many applications. We've talked about it this whole week so far. Just touching on a few are in the robotic industry. So a strain sensor on a robotic arm, measuring the strain of the arm, or even a feedback system to tell the angle of the arm. There's also strain sensors in civil structures like bridges and beams to detect the strain on them. And they could even be in security systems to detect whether a door is open or closed and just exactly how far open and closed that door is. There's also the human body movement. So in the picture to the top right, there's a patient that has a strain sensor across the knee. So this could be for physical therapy applications, such as bending the leg, and your doctor can get an idea if the patient is doing the exercises at home or not. There's also a smart glove application, and for our team, this is the application that interests us. And so we decided to do a smart glove that would control an RC car. So different types of strain sensor techniques. There is optical out there, shown in the bottom left by Micron Optics. There's also a vibration type, shown in the bottom right, and the vibration one works by, there's a wire in there, and when the strain's applied, the frequency of the wire changes, and you read that frequency and correlate it to a strain. There's also capacitive base, and then the most common is the resistive base, and that's what we decided to go with. And so making a glove, we knew we needed to do flexible electronics, and so some advantages to the flexible sensors are the fit and curve area, such as a finger. They're comfortable for the user and they're lightweight. And so in our lab, we have done flexible strain sensors before using methods like screen printing, inkjet, flexo, and gravure. And we've gone over a lot of the advantages, but what we haven't really gone over too much is the disadvantages to these. And so some disadvantages are there's several hours of preparation and cleaning time that goes into this. There's also material waste sometimes. For example, in screen printing, there's always going to be some ink that's left on the screen that you won't be able to use. And over time, there'll be a variation in ink parameters, such as viscosity, surface tension, and density. And so with laser parallelization process, we can try to eliminate some of those disadvantages. So the advantages for the laser parallelization process are simple fabrication. This means you can change your design very easily because it's digital. There's also very low preparation time, and there's also no inks needed, so it's very good in material cost. And how the laser parallelization process works is we start with a polyimide tape, and then with the laser we burn just the very top layer of the polyimide tape, which leaves behind a carbon trace. That carbon trace is conductive, which a signal can go through. To make a larger area, we just repeat this process in vertical lines. And there are four main parameters for adjusting the parallelization: the power level of the laser, which would be the intensity, the speed of the laser, how fast and slow it goes, and then the frequency that it pulses at, and the focal length. And so The top photo there, you see what an example of good carbonization looks like. It's a fully black layer. And on the bottom left, you see one example of bad carbonization. This is an example of not enough power or moving the laser too fast because there is some area that didn't carbonize. And then on the right is the other type of bad carbonization where you actually apply too much power or you move the laser too slow and you rip right through the cap and tape. And so our design is a 5 centimeter by 1.5 centimeter sensor. The arms of it are a 0.5 centimeter width, and each line is separated by 60 microns. Why we did 60 microns is because the diameter of our laser is 60 microns, so spacing those out evenly, we continue the conductivity. The materials used was the universal laser system with the CO2 laser attached. We also used 0.1 mil thick cap and tape, and our PDMS structure was a 5-part elastomer base and a 1-part elastomer hardener. And then we used some N-heptine solution in the mixture to help with the transfer process. And then finally a conductive epoxy to apply the lead wires. So the fabrication process starts with laying down the cap and tape onto, we used a metal object, then putting the metal object into the laser system. And for this type of sensor, we had a power setting of 7.5 watts, a speed of 0.5 meter per second, a frequency of 1,000 ppi, and a focal length of 20.3 millimeters. And then after we have a good carbonization, the next step is to transfer that to the PDMS structure. So to prepare that process, the first thing we do is submerge those sensors in N-heptine for 30 seconds. This allows for better transfer. Then we tape down the sensors into an aluminum mold, and we start preparing the PDMS structure, which I said was 5:1. And again, we add a little more N-heptine to help with that mixture process. Once the mixture is complete, we just pour it on top of the sensors and then put it in the oven for 2 hours at 70 degrees Celsius. And when it's done in the oven, after we let it cool, the PDMS and the cap and tape just pull apart like a sticker, but you have to go very slowly or else your transfer won't be successful. And then once you have the PDMS by itself, then we just cut out each sensor individually and connect the leads using the conductive epoxy. We did a surface characterization of the sensor using the Broker Contour GTK. So from this we found that the carbon roughness was 3.73 microns and that the carbon sat just under the PDMS. And for our experiment setup, since we're developing a smart glove, we attached each sensor to the glove using a Velcro tape. Then we 3D printed a hand and attached a stepper motor to the bottom of it to pull the finger so we can get precise angles with our measurement. And so for our test, we bent the finger 5 times, and each bent was 19.1 degrees, and the terminals of the sensor were connected to an LCR meter to record the resistance. And so our results are shown on the right, and what we noticed right away was for these sensors there is a break-in period that occurs, and so before breaking in there's a maximum change about 22 kilo ohms, and then after we hit about 40 kilo ohms, which is a 45% increase. And so to break these sensors in from now on, what we do is we do a linear stretch 5 times, and we've noticed that if you go more than 5 times, it doesn't affect it too much more, so we just stop at 5. We also did an open versus closed finger test. For this, we tested 7 sensors. Picture A shows the base resistance of the sensors, which was averaged to 1.4 kilo ohms. And then figure B shows the closed finger resistance, which averaged to 245 kilo ohms. And so this gave an R over RO of 171 on average. And so now for the smart glove implementation for our RC car, we attached 4 sensors on 4 fingers because there's 4 main controls, forward, backwards, left, and right. Each sensor acts as a potentiometer, so they're set up with a voltage divider where our microcontroller is reading the voltage drop out long. These are then sent to the RC car through a radio transmission. The RC car then gets these values, puts it into each sensor's calibration curve to detect where the finger is located to move the car forward and back, or left and right. And so this video shows a working demonstration of the product for a right-handed glove. So what you'll notice is the thumb here will move it left, the middle finger will go to the right, the index finger will go forward, and then the pinky will go in reverse. And so a conclusion in future work, laser carbonization for strain sensors is a really good choice for prototyping, is what we've decided, because it's low material cost. If you ever need to change your design, you can do that very easily without buying extra hardware. And it's a relatively quick process, takes about 30 minutes, and then 2 hours in the oven, but during those 2 hours you can be doing something else. And we've also, laser carbonization for strain sensors provides very large resistance changes, so it's very easy for microcontrollers or any other electronic readout to read. For future work, we still need to investigate the lifetime of these sensors and also the drift of the sensors after a certain amount of high cycles, and then also experiment with other more compact designs. So thank you.
Thank you. So we got time for questions.
Yeah, just a question on the braking mechanisms. I wonder whether you have investigated the significance, what happens at the morphological level, for instance.
So the last one again.
I mean, for the break-in, what is the actual significance?
The actual significance. So between a non-broken in one and a broken in one, the sensitivity changes. So we noticed it was about 45%. But after broken in, we've had the glove for about a month now, and we've noticed the changes are still the sensitivities are still the same.
The sensitivity is linked to the morphology of the film, or what is the actual, what happens in the sensing layer?
In the sensing layer. So
I wonder whether you have investigated actually what happens in these 5 cycles.
What happens? So
Why the sensitivity changes?
Because of the break-in theory? We think it's to do with the elastomeric properties of the PDMS. So this is 5 to 1. Maybe if we used 10 to 1 or 16 to 1 or even lower to 3 to 1 or 2 to 1, it might either be doesn't need a break-in process, or maybe still does. That also could affect the hysteresis that you see going on there too.
You one.
What about the reproducibility of the measurement of the resistance that you have? I mean, you do the laser parallelization, but are you sure if you repeat the same process with another substrate, you obtain the same resistance?
No, we are not sure. We have not tested that yet.
Okay.
All we've tried so far is transferring to PDMS.
I had a last question actually connected to the one of Vincenzo. I mean, you're saying by laser you're actually carbonizing, but do you really know what happens there? I mean, carbon is a very general concept. What are you actually getting there? Is it graphitization, amorphous carbon? Because, you know, the conductivity changes a lot according to what you actually form there.
actually getting. But like I said, this is a very new device to us, so what we would definitely look into.
Yeah, exactly. Okay, so I'll now thank all the speakers of this session. Thank you very much. And I'll hand it over to Ravinder for the conclusive remarks.